this video, I'm going to be working with very high DC voltages. The voltages and devices I will be showing today can be very dangerous if you don't know what you're doing, even deadly. So please, if you are following along and think you want to do something like this on your own, if you don't have experience, if you don't know how to work around high voltages and how to be safe, just don't do it. Your safety is not my responsibility. Here's the boost converter. Little tiny unit. It's about 20 bucks Canadian. This is going to be our high voltage supply, our B plus supply. Your 12 volts DC goes in here, and your high voltage comes out here. Some things about this converter. Again, 12 volt DC input, variable voltage output on a trim pot right down in here. 200 to 450 volts DC out. It's very stable. Any fluctuations in power, it just stays rock solid at the voltage you put it at. That's going to be awesome. The other thing is, because adjusting that voltage doesn't do anything to change the voltage on the heater filaments, it's like having power scaling built in. So I can reduce that power, make it a little more spongy, make it break up a little earlier, or I can boost up that power. I don't intend to go any higher than 350 volts here. I probably will put a sticker on this saying don't go higher than 350 volts. As I said, the capacitor I'm using is 100 microfarad rated for 450 volts DC. So if we went full voltage here, we'd be pushing this capacitor pretty hard. The output can be 70 watts. I think that's 70 watts peak, and a few people on the internet who I've seen would agree with me. And it's all your marketing speak. If 40 continuous is good, but you got 70 peak, say 70 because everybody will think it's better. I saw one guy who did some testing, and he estimates that this is good for 40 watts continuous. So when you do the math on that, at 200 volts, that would mean we wouldn't want to draw more than 200 milliamps. At 450 volts, we wouldn't want to draw more than about 89, 90 milliamps. Since we're only powering one 12AX7, it's probably both sides of that triode combined aren't going to draw more than 3 milliamps. So we've got lots of headroom on this. But let's wire this in without a load, and let's just see what our voltage looks like. These are my output, my voltage outputs here. I'm going to be very careful. I'm just going to leave them there for now like that. So we don't want to touch them because they are high voltage. I just want to see when I turn this on what it does to our switch mode power supply, the external supply, what our voltage is here, and how much current we draw here, even though there's no load on here. So again, I'm going to be very careful not to touch these two wires. As a matter of fact, I am going to put these in on the unused side of this breadboard, just so I don't have those bare wires sticking out anywhere. I'm only going to touch this with one hand because we got high voltages here, and we're going to look at what happens when I turn this on. So got a blue light on the boost converter, and the strip, the LED, the heaters, everything is lit up. Everything is looking great. So everything so far is working fine. We're at 11.4 volts. That's still good enough. And with everything idling and no load on the boost converter, we're drawing 294 milliamps. I didn't look what that might have spiked up to when we turned it on, but we're good. We've still got well over 4 amps that we could pull on that power supply. So I'm going to turn this off, let everything wind down, let the charge drain on this supply, and then I'm going to connect my multimeter and measure the voltage on the boost converter. It should be discharged already. So I'm going to turn this to 1000 volts DC because we could see anywhere from 200 to 450 volts. So turn that on. We got our lag. Okay. We're at 304 volts, which is good. I set it to that when I was playing around with it earlier. As I say, this is rock solid. It's just staying right where it should. We've got this trim pot here. If I turn it counterclockwise, and again, we have no load here, our voltage starts to drop. And this trim pot has a high turn ratio, so we can actually really fine tune this. So let's just turn this and see if we actually do get down to 200 volts or even lower maybe. It's a lot of turns. 210. Yeah, it's stopped changing and we're right at 201 volts. Wall voltage is a little high, so probably counts for that extra volt. So we can go down to 200 volts here. That's good. I won't run these plates at a lower voltage than that because I want a lot of clean headroom. This is a bass preamp. We don't want it to overdrive, at least not till it gets way up there. So let's start turning it the other way. It's just to show that we do have that range. So there, we're almost back at 300 volts. 400. And there, we're at 450 volts. I'm going to take this back to 300. I just figure that's a good spot to work with this. You can really fine tune this. You can just nail the exact voltage you want. This is such, I'm so impressed with this. So there we are, 300 volts with no load. I'm going to turn this off. You can watch as I talk. You can see how fast this starts to drain. We're down 80 volts already. I probably won't need a bleeder resistor on here. We're down to 22 volts right now. So we're good. It's gone down. So I don't have the actual preamp circuit at the point where I can wire it in here and see what happens with a load. I'm going to simulate it. I've done some calculating. I'm going to put a 620k ohm resistor on here just to simulate a load and see what happens to our voltage here. I'm using a quarter watt. I don't think this is going to dissipate even close to a quarter watt of power. But if this starts to draw too much current and go too high, I'd rather have this resistor burn than to burn something on this converter. Let's see what happens. Watch the meters, watch the resistor in case it burns up. We want to make sure we get our blue light on here. But let's see what happens. Okay. The resistor smoked. Again, that's why I used a quarter watt resistor. I would rather have that resistor burn up than kill this. I'll do the math later and maybe try and figure out why. Hey, Future Jag here. So what went wrong? I was using a 620k resistor for that test, and the output voltage the voltage I was putting across that resistor was 300 volts. Did I underspec something? So the first thing to do is to calculate the current I should have been drawing through that resistor. So we had 300 volts across it, and it was a 620,000 ohm, 620k resistor. That means we were only drawing 0.48 milliamps, half a milliamp of current. Okay, not a lot of current. It should be able to handle that voltage. So why did it burn? What was the wattage? What was the power we were dissipating through that? So we know we had 300 volts across it. We had half a milliamp of current being drawn through it. So voltage times current equals watts. So we will just round that up to 5 milliamps of current. 300 volts times 0.0005. So half a milliamp, or 0.0005 amps. We get 0.15 watts. That resistor should have been dissipating only 0.15 watts. It was a quarter watt resistor, so 0.25 watts it could have handled. I puzzled on that. I stayed away from this for a couple of days. It's a couple of days later now. And just wondering, is there something wrong with the boost converter? And finally I just thought, well, I got to find out what's going on. So I'm down here. So as I said, I used a quarter watt resistor. All the calculations, everything say it should have been fine. So what happened? Well, as the marquee said earlier, the problem was somewhere between the camera and the chair. When I came back down here, I went over to my bins to get another resistor to try a test. And I had left the bin pulled out when I went and got the 620K resistor, and I saw right away, oh, 20K resistor, and looked at the burned resistor, and I could just barely see the red band at the one end, so 2. So I definitely didn't have a resistor that started with 6, it started with 2, so the drawer was out, it was a 20K resistor. So if we do the math on that, we have, again, 300 volts, and we divide that by 20K resistor, 20,000, we were pulling 15 milliamps through that. So 15 milliamps, 0.015 times the voltage across it, 300 volts, we were pulling 4.5 watts through that little quarter watt resistor. So that's why it burned. So Mr. Dufuspants, honest mistake. That's why we do things to be safe around high voltages, work with one hand. Often I'll not even be sitting on a chair. The idea being that if I get walloped with something, I'll get thrown off the circuit will break, and I might get a bang on my head, but I'll be safe. So after that happened, my first concern was, did I burn something else out? As I said, I used that little quarter watt resistor so that it would burn out before anything else. And even though I picked the wrong one, it did its job. That's what it should have done. With 4.5 watts going through there, that resistor should have burned and basically protect everything else, just like a fuse. So I did, though, want to make sure that I hadn't damaged anything else. So right after that, I did disconnect the burned resistor and the connectors for it, and just tested that everything else was still good. I still had the pilot light and the strip light and the heaters on the supply side, and I had just the boost converter, and everything was fine. Here's that footage. All right, we've got it all wired up, no load. We should still get our 305 volts here if we didn't burn anything out. Turn that on. Yeah, we got our light there. We got 305 volts here, so it has crept up. So wall voltage probably went up a little bit. Sitting at 300 milliamps here. So after that experience, I was pretty sure I was on the right track, and my confidence was restored. So I was ready to actually do a more real-world simulation, or a test of what might really happen with this equipment when I connect the actual preamp circuit. But before I did any of that, I wanted to do a little bit more due diligence, make sure I wouldn't do anything that could damage the converter or the supply. And I wanted to get a closer idea, how much current I might be drawing through from the supply, from the switch mode supply, the wall brick. That can provide up to 5 amps of current. I don't think with drawing, I'm expecting to draw somewhere around 3 milliamps on the output side. I don't think we'd come anywhere near 5 amps of current, but that was just guessing and assuming. How do I figure out if I'm expecting a certain current at the being drawn on the output of a boost converter? What is that going to translate to for current draw on the supply side? If you recall, a boost mode converter is a step-up converter. It steps up a lower voltage to a higher voltage. In this case, we're going from 12 volts up to anywhere from 200 to 450 volts. You never get a free lunch. There's always a trade-off. When you step up voltage in a device such as this boost mode converter, you reduce your current capacity. You reduce the amount of current you can potentially draw from that. So with 5 amps available on the input side coming from the supply, we can only have a maximum that is less than 5 amps. But how much less? I don't know. So I did some studying, and I found that there are 2 equations you can use to calculate supply side current requirements for an expected voltage and current draw on the output of the boost converter. The first equation is called the power balance equation, and it's the more accurate of the 2. So the power balance equation, and I'm going to read it, it says your input current will be equal to output current times your output voltage divided by your input voltage times 1 over the efficiency plus the output current times the peak-to-peak current ripple. No. So That's a lot of stuff, and I was like, okay, two things that I have to make assumptions about. I don't know what the efficiency of the boost mode converter is. And I also don't know what the peak-to-peak ripple is. As I said in the last video, a boost mode converter can have an efficiency of 85 to 95%. I assumed that maybe this one isn't that efficient, so I just arbitrarily chose efficiency of 75%, and I assumed a peak-to-peak ripple of 30%, and that was kind of based on some things I had seen other people doing with similar converters and doing these similar sorts of equations. So plugging that all into the equation, I won't say it all here, all the numbers. For a 3 milliamp current draw on the output side, the supply current draw will increase by 100 milliamps over whatever we're already drawing. If we're drawing nothing, we should see a 100 milliamp draw. If we're drawing 300 milliamps, once we turn on the boost mode converter with the load, we should see a 400 milliamp draw. So that's using the power balance equation, the most accurate equation we can use. There's another simpler equation that's not quite as accurate, but still very, very close. And that's just the power balance rough estimate equation. Using that equation, we only have to make one assumption. We know our output current draw. We know our output voltage, we know our input voltage. The only thing we don't know is efficiency. So the rough power balance equation says that your input current will be equal to your output current times your output voltage divided by the input voltage times the efficiency. So much simpler, and again, we only need to make one assumption, that's efficiency, and I'm still sticking with my assumption that this will be a 75% efficient unit. So plugging that all in, I get 0.003 times 300 divided by 12 times 0.75, or 0.003 times 33.3, or 99 milliamps. So even though this is a rough estimate calculation, it matches closely enough to the longer equation, which came out with 100 milliamps. We're 99 milliamps with this. So we're expecting we're going to draw 99, 100 milliamps from the supply side when we fire this up. As a little sidebar on that, the supply side fuse on the boost mode converter is 10 amps. There are chapter markers down below if you don't want to get into some more math right now just to figure out why it's a 10 amp fuse. Go to the chapter markers and just skip to the next section. We're talking about such a small fraction even of an amp, 100 milliamps on the supply side. Why is there a 10 amp fuse in here? Did they just throw that in so it would never burn up? And the answer is no. The fuse has to take into account what the maximum peak draw could be. So not even continuous draw, but any spikes. You don't want that fuse burning out just because of a brief spike. That's why there are slow blow fuses, for example. This supply is rated at 70 watts peak, and it can output anywhere from 200 to 400 volts. Remember that as we increase the voltage that we are putting out from the converter, our capacity for current decreases. To figure out why this has a 10 amp fuse, we need to sort of figure out what would be our maximum conditions we would run this under. So if we assume that we are going to have a 200 volt output, we're going to be drawing 70 watts of power, so we can calculate the current draw that equates to that. Using the power balance estimate equation, we can estimate how much current we would be pulling on the supply side. So with to figure out, first of all, the current that we would be drawing out, wattage equals voltage times current. So to figure out the current, if we are dissipating 70 watts, that's the maximum peak on this unit, and we are doing that we are powering a load with 200 volts, our current would then be 70 divided by 200, and we would be drawing 350 milliamps. So on peak spikes, your maximum current draw would be 350 milliamps. So taking those numbers that we have here now, we can calculate what the maximum input current draw would be. And again, this would be peak, not continuous. That would be 0.35 times 200 divided by 12 times 0.75. So that ends up being 0.35 times 22.22. So 3.5 times 22.22. If we're drawing 350 milliamps output from the converter, the supply side is going to need to give us 7.78 amps. So that's why the fuse is at 10 amps. Hope I didn't bore you with that. With all those calculations done, we're ready to test this, and I'm going to test it with a 100K load. I'm going to put 300 volt output, because that's roughly what we're going to use with the when we get the preamp circuit in here. And I want to simulate the load of the preamp circuit such that we're drawing about 3 milliamps. I arrived at using a 100K resistor just by doing the math. If I take 300 volts and I divide it by 100K, 100,000, that comes out to 0.003 amps or 3 milliamps. So a 100K resistor should simulate what I'm expecting the preamp circuit to do in here. At least for our testing, this will give us some good numbers. What rating does that resistor need to be? How many watts will that resistor dissipate under those conditions? Well, we are saying it's going to draw 3 milliamps, 0.003 amps, and it's going to have 300 volts across that resistor. So 0.003 amps times 300 volts. It's going to be running at 0.9 watts. So we want a 100K resistor that's at least 1 watt. I always like to double those things. Rule of thumb is double those things. So we want a 100K 2 watt resistor. Maximum continuous power, we talked earlier about peak power. Earlier, I estimated that maximum continuous power, in other words, you could continuously draw without a break, is 40 watts. At 40 watts, we could draw 200 milliamps and still be comfortable. So we've got way more capacity than we need, or at least we should. So over to the bench, we'll do these tests and we'll see how it looks. Okay, I've got everything rigged up on the bench here. I'll just detail what's going on. So this meter over here is registering the current draw on the supply side. I'm not monitoring the output voltage on the supply side. We know it stays at 11.5 to 12 volts, so we're good there. This meter is measuring the current draw on the output side of the converter, so on the load, what we're drawing through the load. And this meter down here is going to be measuring the voltage across the load on the output side. So input current, output voltage. I won't detail how I've rigged all of this. I have done everything, rigged up everything as safely as possible. I've got heat shrink around any connections I've made where I can do that. And again, because it's high voltages, I'm going to be working with one hand, and I will be safe that way. As far as the circuit itself, we have our supply voltage coming in here, 12 volts. I do still have the pilot lamp, the strip LEDs, and the heaters on the 12AX7 connected. They are part of the load, and we want to see what our total current draw is going to be. So I need those connected as well. So for the start of this test, I'm not going to have the boost converter in the circuit. To put that in, I will just take this little jumper and put it right here on the other side of the 100K resistor, and that will complete our circuit through the meter that's registering the current. But to start off, just so we know what our load is before the the boost converter is in play, we'll have this disconnected. So that means it will show us what our current draw is of just the pilot lamp, LED strip, and heaters. So plug everything in, get everything ready to go. I've got my power bar turned off right now. That's sort of my main switch. Turn the power bar on, and you will see shortly that we're drawing current on the input. We've settled at about 300 milliamps. So just give that a little bit for those heaters to get right up to operating temperature. But you see we've got zero current draw from on the meter measuring the boost converter, and we've got zero voltage, and that's because I have not completed that circuit yet. So it's been long enough. We're drawing 300 milliamps. With just all the low voltage devices. So now we will connect the boost converter with the 100K load, and we'll see how our current draw changes on supply side, what we draw on output side, and what our voltage is on the output side. Connect that in. And now you can see we have got 303 volts across the resistor. We're drawing 3.1 milliamps, and we've got 400 milliamps total draw on the supply side. So our calculations were bang on. When we put the boost mode converter with the load in there, our current increased by 100 milliamps. Everything is looking great. We got the 3 milliamps we expected. We are still seeing 303 volts on the output. The voltage has probably changed at the wall today. So everything is looking really, really good here. Let's see, I talked earlier about I probably won't need a bleeder resistor. A bleeder resistor you put across your load, very high value resistor, just to bring any stored voltage down to zero as quickly as possible. And I said I don't think I'll need that. So watch the meters again. In particular, watch the meter that is reading the output voltage, and see how fast that goes down to zero. So it dropped down to nothing. It dropped down to zero in a matter of 3 or 4 seconds. So no, I won't need a bleeder resistor on this either. The power, once you remove the source, this whole system goes inert very quickly. So the only other question that I have left to answer, because my calculations were so close to what actually really came out, and I had made an assumption on the efficiency of the unit, it actually looks like my assumption was correct. But now we know what our input current is. We can actually figure out what the efficiency of this unit is using the efficiency equation. So the efficiency equation just says your power out in wattage divided by your input power wattage times 100 gives you your efficiency. So for our power out, we had 300 volts across the resistor, and it was drawing 3 milliamps. So 300 times 0.003. So we were drawing 0.9 watts. Again, matches our calculations. On the input side, we had 12 volts, and we were drawing 100 milliamps. So 12 times 0.1 means we were dissipating 1.2 watts on the supply side. So 0.9 watts output side, 1.2 watts input side. We divide 0.9 by 1.2 and multiply that by 100, and our efficiency is 75%. So lucky guess. So 75% efficiency is low. I assume that has to do with the parts that are used in here. I'm not really too concerned about that. I'm getting what I want to get out of this. Nothing is hot, nothing burned, nothing is running over its rated spec. So I think we're good to continue. So that's about all the time I have for today. So what have we done? We've established that I will use the switch mode power supply and boost converter. The switch mode power supply will give me my voltage for my low voltage components, the LED pilot light, the LED strip, and the heaters of the 12AX7. And it will also provide the 12 volts to the boost converter. And the boost converter's only job is to provide B plus to the preamp. So 300 volts, I'm estimating it can support up to 200 milliamp current draw, and I don't think we're going to draw that much current. Like I say, I think we're only going to draw about 3 milliamps. So that's the only unknown. What's going to happen when we put the actual load on here, but I'm confident everything's going to go okay. So we have now reduced the cost to build one of these, although I've already spent the money for building it with a traditional power supply and all that anyway. I can use that stuff somewhere else, and I bought two 5-volt switch mode supplies and the other LEDs, but those things can get used somewhere. What we've established is we can build this much more cost effectively. It's going to take up much less space. I'm still going to put it in that larger chassis. But if I build another one, and I'm leaning toward building something for guitar at some point after this is done, I can build that smaller, maybe even in a largish pedal box, kind of tube driver size, BK Butler tube driver size. Anyway, we'll see. I'm really excited about this. So I think we're good. We're going to move ahead. I know how the whole design is going to work now. There will probably be tweaking once I get it working, but let's get it working first. Next video, I think I have to drill the chassis for all the components and everything, so that I can mount these things, the board and the converter and the filter cap and all of that, and then I can, in the video after that, I can hopefully wire it up or get it mostly wired up. Video or two after that, sort of 3 videos down the road, I'm hoping we fire this up and we can see what's going on and maybe even hear how it sounds. I'll scope it as well. We'll look at what's happening with the signal. We'll put a 150 millivolt 1 kilohertz signal in and see how our signal looks going all the way through to the output. Maybe we'll put a loop or something on there and put it through through my interface in here and see how that sounds. I don't know. So you pretty much, the next video will be drilling the chassis. Video after that we'll start soldering, maybe finish soldering. If not, it'll be the video after that. I do have to build a case around this. So that'll be another video, and I've got some plans for that as well. So I'm rambling. Anyway, I am very excited. This was a really fun day for me, doing all this and learning all of this. Like always, thanks for watching. Please like and subscribe. Check my band One Soul Thrust. The links are in the description below. And until the next video, we'll see you.